Okay, good afternoon or good evening, everyone. My name's Richard Kennison, and as Shinmar said, I am the Senior Designer for Race-Tec Sealing Limited. And what I'm going to do today is give you a presentation on some of the high-performance sealing products that we simulate using the MSC Mark software. Just a little bit of an overview about the company I work for. I work for Race-Tec. We're part of the Rollway Group, which was founded in the 70s, and Race-Tec has been around since about 1995. Group-wide, there are 200 personnel, and we're separated into 4 distinct companies. We have Blue Diamond, who manufacture components for the rebuild market and other types of components. We have PTF Engineering, who are experts in stainless steel welding and get involved in the petrochemical market. And we have Stella Meta, who produce biological and nuclear filtration systems for the MOD. Now, I work for Race-Tec, and we're primarily involved in motorsport applications. We're a very well-known supplier within the motorsport market. We work very closely with a lot of the F1 teams, as well as other forms of motorsport, supplying high-performance seals, high-performance CV boots, and other hybrid rubber molded components. So the first topic I'm going to talk about is analysis of a hydraulic accumulator bladder. So accumulator bladders are used in hydraulic systems, so the pump size can be reduced and retain the ability to cope with extremes of demand. The supply circuit can then respond more quickly to sudden changes in demand, which, as you'd understand, in motorsport could be very important, and the system pressure fluctuations are smoothed and damped. The hydraulic side can be fluid, hydraulic, or water. There's a few images at the bottom of the screen showing a typical component contained within an alley housing, a section view for a component, and then some nicer images of some of the accumulators on their own. So accumulators are made up of 3 components. We have a rubberized element where one side is connected to the hydraulic system, and the other side is a closed element which contains nitrogen precharge. Now the precharge is set depending on what you're trying to achieve with the accumulator. The accumulator is compressed on its retention bead. An initial precharge is applied to the nitrogen side, which expands the bladder out to the housing, and then hydraulic pressure is forced in through this port, which causes the deformation and collapse of the bladder. So we're particularly interested in what happens, what stresses are occurring during this deformation. So why do we carry out these type of simulations? We know from experience that when an accumulator collapses, it tends to go into a 4, 5, or 6 point lobe collapse, as you can see in this image at the top right hand corner. What we need to ensure that is this collapse does not cause stress and strain problems between the maximum and minimum system pressures. You're always going to get a tri-lobe collapse of some sort, and there's not a lot you can do to limit it, but you need to be able to monitor and see exactly what stress conditions being created. The buckling load and the shape is interesting in this case from a numerical validation point of view. The prediction of the strain that occurs is a key issue in all of the accumulator geometries. It's particularly important in the acorn type accumulators because we have a horizontal split line which runs around the top face of the mold. What we need to ensure is that the highest stress point doesn't occur in correlation with the split line of the mold, causing a design problem. We use this software because it provides us the ability to provide extremely high compression ratios by using the software to predict where failures could occur and selectively eliminate them. So what are we looking at in terms of this analysis? We're comparing a numerical result to a physical test. We're looking at the buckling mode, the buckling pressure factor, or the initial buckling pressure, and the post-buckling behavior. In addition, we're also looking to compare the strain values with the known material maximums, so we can see that we're using the material within safe working limits. So what we did in order to be able to visualize the deformations, we created our own special transparent case, as you can see in the image. We gradually apply a vacuum to the internal surface or the nitrogen surface to draw the air out of the accumulator, causing it to collapse. We found that you get an initial pressure buckling at around about 0.0022 megapascals. Now, in terms of accumulator simulations, you don't actually have to simulate with pressure on both sides. What you're actually looking at is the pressure differential. So all we needed to do was simulate the collapse rather than actually the operating pressures, because the stress condition is the same. The analysis applies therefore a pressure difference as a vacuum condition to the internal surface of the accumulator, causing it to collapse on itself, and we're looking at the differences between the two. Material-wise, we need a hyperelastic material model based on strain energy formulations, either Ogden or Mooney, and you need to obtain material coefficients across the correct range of stress and strain. So we started off with a tensile test using a constant uniaxial stress rate, and we also carried out a compression test, but we carried this out in biaxial state rather than compressive state, as you'll find you'll have issues with material data being affected by friction. We used the inbuilt experimental data fitting curves within the MARC software, and we found that three-term Ogden gave the best strain energy function fit, and it gave a very good small strain fit which we found was accurate for buckling behavior. We actually used the full sweep of tensile compression data to obtain coefficients across the whole range of the test. So here's just an overview of some of the analysis features that we used. Because this is a 3D accumulator, we can actually use an inbuilt function in the MARC software called the cavity function. This can be run in 2D or 3D. We've used it in 3D in this case. Most of the accumulator elements are selected to be part of the cavity, and then you close off the end of the cavity using special cavity elements which are selected from the drop-down box. We could apply the application of gas pressure directly, but the PD characteristics would not have been calculated that way, so we chose to use the cavity definition model. The pressure, therefore, is updated incrementally when the cavity as it's collapsing, which allows us to monitor the reduction in volume as the simulated collapse occurs. We allow MARC to handle contact and friction automatically. We use self-contacts at separation and sliding friction. We found that the bilinear friction model is best for this. It provides a very accurate model of friction in the presence of very large deformations in excess of about 1.5 as a friction coefficient. By experience, we know that the friction between the EPDM and the external surfaces of the accumulator housing is about 0.5, and the friction coefficient in self-contact is about 0.8. However, we also found that a very high pressure barrier starts to exist as the part is collapsing. As you can see in the video, it's contacting at 3 points, and in between these two contact surfaces is a very, very small hydrogen barrier, which is a very low friction coefficient, which allows the component to rotate on itself. You can see in the video that it's collapsing and then starting to rotate back on itself up towards the rigid member. So there are typically 4 analysis steps. We do an installation step where we're grabbing the accumulator and compressing its O-ring seal at the top between the two housing features. We do initial gas pre-charge where we charge the internal surface of the rubber accumulator, which then causes it to form out to the OD body of the metalwork, which for the material testing would be your tensile component. We then do an Ingelval buckling solution, and we're looking at geometric and material non-linearity, and the mesh is automatically perturbed. And we also use the arc length solutions using advanced Kreisfeld methods. In post-buckling control, automatic limits are imposed on the magnitude of iterative displacements. It basically stops the software running away during the iterative procedure and going to smaller and smaller steps. It's particularly useful in this case when we have loose assemblies and very large buckling analysis going on, which involves very sudden and very large deformations, as you'll see from the videos in a minute. It's used in all the subsequent analysis that we use. So here's a comparison between some test results. Using the MARC software, we achieved an initial buckling of about 0.0021 megapascals, which compares extremely well to our physical test result. And there's only 5% difference between the actual values, which is phenomenally accurate for us because it allows us to be 100% confident in what we're doing. So here's some images from the physical test. So this shows an initial buckling, which occurred at the 0.0022 megapascals. There's an intermediate stage where you start to see a curve feature occurring on the side of the accumulator. And then there's a maximum pressure stage where all of the air, as much as possible, has been removed from the internal surface, simulating full collapse. And you'll see that the accumulator is starting to twist on itself. Here's a comparison between the deformed state in the Mark software and the physical sample. You can see that the comparison is very good. It shows clearly the twisting motion. The twist is quite consistent. The only difference we can see is the bottom of the accumulator in the physical test is further up in the axis, whereas the one in the Mark software is slightly more protruded, but we feel that's probably down to slight anomalies in friction coefficients and molding irregularities in the physical part, which can cause more collapse on one side than the other. So here's a full simulation video showing the collapse model, where the vacuum is being used to simulate the compression ratio of the bladder. You can see the deformation that you can achieve. You can clearly see that the Mark software has highlighted that there's no stress on the top diameter of the part, so we know that if we put a split line here, we're not going to cause ourselves any problems with stress propagating onto a split line. Here's a nice X-ray comparison between the different types of accumulator that we manufacture. You can see that Mark software has predicted that it's going to be rotated slightly in a clockwise direction as it's being compressed, and the X-ray image is showing exactly the same function, which is a very good comparison in terms of a simulation and a physical result. So in conclusion, it gives us consistent buckling and post-buckling behavior. It's predicted from all the analysis methods that we used. It gives us the ability to predict with a high degree of confidence the initial buckling pressure, the subsequent deformation we're going to see, and it allows us then to design an accumulator that can handle a much higher compression ratio or design pressure ratio. The maximum strain information that we achieve from the software enables us to reduce the failure mechanisms from an very early on stage, allowing us to tweak how the molds are designed to ensure that we don't pick up a high stress point at a mold split line. However, it's very, very important that your material data is from both tension and biaxial compression state, as they're both equally important in terms of the simulation result. Now, the next example we're going to give is on the simulation of constant velocity joint boots. We supply a large proportion of constant velocity joint boots into motorsport, and we're also very successful in supplying the same type of boots into high performance military vehicles. So the boot is used to protect the joint from the ingress of road grime and dirt, and the boot helps to make sure the joint is fully lubricated and to ensure a long working life. There are two types of standard CV boots, what we call a Christmas tree boot, which is normally molded from a thermoplastic elastomer, which has a nice temperature range of about -46 to about 125 degrees C. For motorsport applications, we design using a special compound that we develop, which is very abrasion and tear resistant, and that allows us to work from about -46 again to about 180 degrees C. In motorsport applications, the deformation angles are a lot smaller, so it means we can compress the design quite significantly. We look at these type of simulations because we want to ensure that there is no self-contact as much as possible within the boot, which is likely to cause heat build-up, and there's actually no contact with the vehicle body or any of the bodywork around the boot area. This is extreme angular articulation can cause a phenomenon that we've called popping, which is when the CV boot actually comes away from the shaft and starts to form out on itself. This can be caused by grease loading or lack of contact forces on the shaft. We use the software to ensure that we predict the strain level. We're looking at ensuring that the boots retain themselves on the drive shaft without the need to use tie wraps or circlips, as in applications where space is limited. You can see that tie wraps and retention clips can cause contact with the rubber and can cause failure to occur. So we use the software to make sure that we've always got sufficient contact forces across a range of temperatures. and it allows us with a high degree of accuracy to predict the exact post-articulation deformation angles, which means we can supply this on to teams and customers, and they can use this in their airflow models to check airflow around the boot. So here's some more general analysis features used for boot simulations. We let Mark again handle self-contact, sliding and friction. We use a new function in the contact table called penetration, which is a new feature for 2013. We also used again the bilinear friction model. We define the friction coefficient between the CV boot and the shaft, and maybe the tri-lobes as being about 0.3. There is a special friction condition for self-contact, but unfortunately that's covered under an NDA agreement, so we can't release that information. We can also look at wear in unlubricated self-contact, but again, unfortunately, that is also covered under an NDA. But the software is capable of simulating this type of thing. So for boot analysis, we normally have 3 analysis steps. The boot installation onto the rigid shaft. As I say, since 2013, this is now completed using a penetration tolerance in the contact table. In previous versions, the only way you could achieve an installation of a rubber component, such as an O-ring, or anything you need to stretch up onto the sides to show installation, you'd have to use a rigid grow body, whereas now you can actually specify a penetration tolerance and apply a load table to it, and during the first load case, the Mark software will automatically expand the rubber element to touch the rigid surface body, which is a very, very good improvement. It significantly decreases the run times. We then look at shaft articulation, so that's steering and droop suspension. We look at plunge if it's a plunging joint, and steering angle if it's a steering joint. These are all controlled by load tables using the normal contact table analysis methods. The exact method that we actually use for doing the combinations of these features is something we tend not to disclose, as we find it gives us quite an advantage. You can also then apply a final load case to look at the rotation. So as long as you know the mass of the rubber that you've manufactured from, you can run a self-centrifugal effect on the rubber to see what the deformation due to rotation is going to cause. You can also apply grease loadings by selectively applying mass in contact areas behind the boot, and you can apply the rotational effects to this as well. So here's a nice video of popping analysis, which is something you don't want to see on a CV boot. See at the start of the video, the boot is being expanded to the shaft size. We have an angular deformation, and then as the speed comes on from centrifugal force, the boot draws itself forward. This area here is protruded, and that's not something you want to see for a CV boot, because this will rotate with the joints and it will cause a build-up of heat and damage. Let's just play that again. So the boot increases to the shaft size, angular deformation, centrifugal force. You see the boot has popped forward. Again, we try to eliminate this if all possible. This can be eliminated by increasing the contact force on the shaft, or increasing the material properties, or stiffening the material up. Here's a full analysis simulation video of a different type of boot. You can see the boot is expanding to the shaft size, angular deformation, and then finally a steering motion. This is great for us because we can see exactly what the boot's going to do. We can see areas where we have too much material or not enough material, so we can actually refine the design to make it as small as possible. So in conclusion, on the CV boot analysis, it allows us to predict with a very high degree of confidence the ID tension, so we don't need to use tie wraps and retention clips. We can rely on the force produced by installation alone. It allows us to predict the deformation after articulation, which we can supply to our customers and allow them to do airflow analysis. Or we can also look at the centrifugal effects from the mass of the component itself, as well as the grease loading, which can be very important in some high-speed applications. By monitoring the strain information, we can reduce failure mechanisms again from the very early design stage. And it allows us to run through designs in a virtual environment rather than making tooling and testing. It allows us to predict and eliminate the non-desirable popping case, which is not something you want on a CV boot. But again, accurate material data is essential, be it that at the right state of stress and strain or temperature. And you also need to have a knowledge of the application anomalies that you see with certain types of joints, as that can cause significant issues. One final application area that I was going to share with you was the analysis of rotary shaft seals with wear. We use a user subroutine which allows us to predict the level of force and therefore the level of wear that occurs on a seal during operation. It allows us to predict using the software the exact lick force, and then using the lick force and the user subroutine we can actually predict with a degree of confidence the life that the seal is going to attain. However, you need to be very accurate in your material data for your wear conditions and ensure that you've tested a comparable Hertzian contact condition. Simply using the standard pin-on-disc type materials for something in a rotary motion is not going to give you the right result. We found by experience that the RCOD standard wear law is not really sufficiently accurate for viscoelastic compounds, and that we've worked on reviewing our own version of this with some external testing. The last couple of slides are a comparison between the two. So on the left-hand side, we have a standard seal simulation, which is showing the wear that occurred after about 5,000 hours. You can see that the contacting element has worn down. And on the right-hand side is an image of a section through a seal that's been tested for the same period, showing a similar sort of wear. There are slight differences which are likely due to material anomalies. The simulation was carried out at 25 degrees C with the testing of the generated heat, so it would deform more, causing more contact area to establish. And the last slide is just an overview of our website showing some of the components that we've been involved in. This is a page on drive shaft boots showing some components that we've manufactured in the last few years. There's a section on accumulator bladders which gives some information on specifying them and how they work. There's a section on anti-vibration mounts, which is something we're working on using the new version of the Mark software, as they've introduced the ability to import dynamic modulus, storage and loss data. Precision mouldings. And seal plates and moulded gaskets. And at that point, I'll hand back over to Shinra.